begin. Our next speaker is Eshita Mazumdar, who will talk about zero-sum theory. So, please.
Yeah. Yeah, thanks a lot, Professor Nathanson, for giving me the opportunity to present my recent work here in front of you all. So, my main research is focused, throughout that, I'm focused on the combinatorial number theory and that to zero-sum theory. I worked on uh, many a direction of zero-sum theory, but which attracts me a lot is to go from the abelian to non-abelian structure, and I find that there are very interesting things are there. So I start my talk with a little bit of introduction of zero-sum theory for the abelian setup, and then I will try to move further for the non-abelian case. This zero-sum theory was mainly motivated by the work of Paul Erdős, and the whole study has started in 1961. So there was a trivial observation which one can notice is the following: that let's say I'm considering any, any n numbers, so the repetitions are allowed over there, okay, and integers I'm talking about, and then I can conclude that there is a subcollection whose sum is 0 modulo n. That is it is divisible by n. Okay, and one can conclude this observation very easily simply by considering a new sequence, where my BIs are A1 plus A2 plus up to AIs. Okay, and you just see this number over the cyclic group of order n, and you know that we have n numbers. So either all are distinct or two of them are same, and that will conclude that, well, you will always have a subcollection whose sum is divisible by n. Now, interestingly, this length is a very much important here, because one can see that if I consider the sequence of this kind where my 1 appears n minus 1 time, then you won't find any subcollection whose sum is divisible by n. So this length n is the tight enough. Now the question is that what length will guarantee me that I will have a particular length subcollection whose sum is 0 modulo n? Can I say on that direction or not? Now the thing is that this is a trivial problem, but when I'm dealing with that, that kind of problem, it will be non-trivial ones. And that was the first work done by Erdős, Ginsburg, and Zinn in 1961. It is a classical theorem which says that if you consider any 2n minus 1 integers, then you will definitely get a subsequence of length n whose sum is 0 modulo n. And interestingly, this length 2n minus 1 is indeed the least length having such property, and you can conclude it with this sequence. Okay. Now, this is the base of the zero-sum theory, and let me just introduce you the zero-sum theory in general setup. So here I'm talking about the integers. So now on, I will consider the groups which are the finite abelian group. The structure imposed on it is an additive structure, and 0 being the identity element of the group. I'm taking FG, the free abelian monoid. Okay, and the elements I'm writing down in the multiplicative nature. So when I say a sequence, it means it's an element of FG. Okay, so it is a multiset of G over G. Okay, and this is a zero-sum sequence if the sum of it is the identity element of the group. For example, if I consider the sequence S to be like this, okay, where 1 appears twice and 3 appears once over C5, then yes, it's a zero-sum sequence. On the other hand, if I consider the other sequence like this, then this over C5 too, then this is not a zero-sum sequence. So zero-sum problems is nothing but to study the condition which ensure that whether a sequence would have a non-trivial subsequence of some prescribed property. That prescribed property could be my length or something else also. So for example, this is to find out the least integer corresponding to the group CN, so that every sequence of that length has a non-trivial subsequence. That is a zero-sum problem. And we know the answer for that. This number, this least integer would be n here. And that is what we have observed in our trivial observation in the first example. Well, now the thing is that if you just, change your CN to any finite abelian group, and you ask the same question that what is the least value of this K? Now that least value I will call as the input constant, and that was introduced in 1963 by K. Roger. So it has been defined as the least positive integer K such that whenever you will have a sequence of that length, it will have a non-trivial subsequence whose sum is zero. So you can say that I have written down in this way. And to guarantee you that it can't happen that all epsilons are zero, that is not possible. Okay, at least some of them are. Okay, so there is, I made some mistake. So please, okay, so it's a, like not all epsilons are zero. Okay. So what it says that when you started, so there exists, I mean, this can be thinking like that. There exists a sequence. You can construct a sequence of dg minus 1 length, and you won't find any zero-sum subsequence. But the moment you will add one more element from the group to the sequence, it forces you to find out a zero-sum subsequence. Well, on the other hand, I can say that since this is the smallest, I can define dg as the small dg as the supremum of cardinality of S. It's the length of S. Okay, is the zero-sum free sequence I'm considering. So clearly dg plus 1 is equal to my this capital dg in the abelian case. Okay, and this value is my n minus 1 when I'm considering small d. Okay, so this result we already have. So currently we will write down everything on the capital D, and later on we will focus on this small. Okay. Now, as I said that, there is another way of thinking which Erdős Ginzburg Ziv has done, is that the length, what happened if I fixed my length? So in his case, what they have done, they have considered a sequence over Cn, and they are focused on the length to be n, that is the cardinality of the group. So, well, so based on that, I'm defining a new constant, which we call as a Gauss constant. So it is defined as the smallest positive integer such that whenever I will have a sequence of length k, there is a subsequence of length cardinality of G such that its sum is equal to identity. And we have seen that for cyclic group, its value will be 2n minus 1. Now, let me just talk about what are the applications. There is a connection to the algebraic number theory. If you consider O being the ring of integers over the number field and G being its ideal class group, then, and if you take X to be an irrational, irreducible element from ring of integer, and if you consider XO the principal ideal, it can be written as the product of prime ideals. Okay, so and DG, okay, so the main port constant of the ideal class group, that is the maximum number of prime ideals appearing in the factorization of an irreducible element in O. Well, for any finite abelian group, we have a general upper bound for DG, which is this. Well, this is not the sharp one. Okay, but with the help of that, in 1994, Alfred Granville and Prominence proved that there are infinitely many Carmichael numbers, which we call as the pseudo primes, and which we extensively use in the study of cryptography. So if we can get a sharper bound, that means we might get a lot of number theoretic result, which will be useful in several other fields. So there is an importance to find out the precise value of this DG. Now let's see that what are the known results for finite abelian group. Well, we know that what happened for the Cn, we know that its value will be n. When I have a group of rank 2, that means of this structure where n1 divides n2, its value will be this, n1 plus n2 minus 1. When I have a finite p group, abelian p group, I can say that its value will be like this. Now, looking at the structure, actually, Olson conjecture, it's a very general thing, that he conjectured that it might be for any abelian structure, its value will be like this. And for several years, we believe that its value will be like that. And, after 23 years of that conjecture, in 1992, Geroldinger and Snyder proves that, well, the conjecture is not true for rank 4 and for rank 5. But for rank 3, we don't have any concrete result as of now, as of my knowledge concern. So yeah, that could be one of the very nice approach to think about it. Interestingly, for the abelian setup, in 1995, Gao has proved that there is a very nice relationship between this this Gao constant and the Davenport constant. So in terms of small dg, I can write down in this way. Now let's move to the case to understand the case that what happened for the non-abelian setup. Well, for the non-abelian case, I'm considering G being, for now on, I'm considering G being the non-abelian group, written multiplicatively and 1 being the identity element. F star G denote the free non-abelian monoid group. So if you take any sequence like G1, G2, Gn, and if I consider any subsequent T star, so T star is a ordered subsequence if I can write down in this ordering only. Okay. So when I say zero sum or product one sequence in the non-abelian setup, what happened? It can be possible that you are taking a sequence from F star G and you are saying it to be unordered product one sequence if you considering all possible product, because you take the permutation, okay, and you consider all possible product. If identity belongs to this set, then we say that your S is unordered product one sequence. Will this set I'm denoting as pi S. And ordered means when I'm considering S corresponding, if I multiply this like G1 into G2 in this way, GK, so I consider it as a pi S one element. This S is said to be ordered product one sequence is this pi star S is equal to 1. Okay. Now I'm taking a sequence. Now I wanted to define the when I am saying a sequence to be product one free. Okay, so what happened in the unordered case? So I'm defining, so you know that what is a pi t here. Pi t is the set of all permutations. So you are taking the all subsequences and considering the corresponding pi t and take the union that I am denoting as product S. Okay, and we say that S is product one free if identity is not there. Now, what happened in case of ordered product one free is the following, that you are taking corresponding to your sequence S, that the ordered sequence S, you are considering the ordered subsequence and you are considering the corresponding product. So we are maintaining the ordering of the sequence, okay? And we consider the union of that. So this is the product star S, okay? S is called ordered product one free if one does not belongs to it. So based on that, I can define my small domain. I'm going to define my small Davenport constant, which is like the following. DG is the supremum of the length of S, so that S is a product one free. Okay, this is for the unordered case. And small ordered the input constant if it is again the supremum of length of the sequence, and this S is a ordered product one free. So you can understand that when I'm considering small dg plus 1, it will give me the least integer such that every sequence of length that has a product one subsequence. Similarly for D naught G. So from here I have this observation. Now, similarly, we can define Gauss constant like that. So it is, again, it is the, least integer, so that whenever you consider a sequence, it has a unordered product one subsequent and ordered Gauss constant. I can define it as like the least integer, so that whenever you consider any sequence of that length, it has an ordered product one subsequence of length cardinality of G. Obviously, this relation holds true here. Now the question is that as if the abelian case, whether this result is true for the non-abelian setup or not. Well, there are certain known results. First result by Olson and White in 1977, it's for the non-cyclic group. They have proved this thing. And for the dihedral group, it's in 2007, Bus has proved that, well, this is the example for the lower bound. He proved that, well, the small the input constant is n, and Gauss constant is 3n, which shows that the relation holds true here. For dicyclic group also, this showed that the relation holds true. Okay, they evaluated small the input constant and the Gauss constant. Now on, I'm considering the metacyclic group of this form. In 2007, for that metacyclic group, Bas has proved that small the input constant will be this and the Gauss constant is this. So one can observe that he proved that, okay, for this metacyclic group, the relationship holds true. And he conjectured this. There is some other observation related to Gauss constant, which has been, Gauss and Lee in 2010, they have conjectured that this Gauss constant would be less than equal to 3/2 of cardinality G for non-cyclic group G. And they prove that for non-cyclic group of odd order greater than 9, its value will be this. Hahn proves that it's true for all non-cyclic nilpotent group also. Now let's focus on the Gauss constant particularly and see that what we did. We consider A to be a finite P group and we consider G to be like this, and we prove that, well, the conjecture which made by Gauss and Lee is true. You can see that this is an even order group. Okay, so that has not been covered earlier. Okay. Now, recently, we consider the metacyclic group where M divides N and M is odd, and we prove that the Gauss constant is smaller than this quantity. So that also proved that the conjecture Gauss and Lee has given was true. So let's see what are the results we have for the small the input constant. Recently, we proved that if we have a finite abelian group A and of this particular form, then this ordered small the input constant is same as small the input constant, and that quantity would be equal to this quantity. We also prove that if we have this relation, but if we consider L to be not congruent to 1 modulo P for every prime P divides N, then again the conjecture Bas has given is true. We consider that for the metacyclic group, if M divides N, then also the conjecture given by Bas, that is true. So we are proving something extra which has not been covered in the Bas conjecture. We also prove that Well, if you have G to be a metacyclic P group, and if you consider E to be exponent of G and M to be cardinality of G by exponent of G, if one of these two happen, that if either G is splits and or G contains a cyclic normal subgroup C such that the cardinality of C is E exponent and G by C is a cyclic group of order M, then we can say this. Okay. Okay, so now you can see that I have introduced an ordered version of the small Davenport constant, and let's see what we can conclude from here. If you have a finite group G, and let us consider FPG being the modular group algebra, the nilpotency index of the Jacobson ideal FPG is called the Lowy length, and which we denoted by LG. Then in 2004, Dimitrov has proved that for any P group G, whether it is abelian or non-abelian, this happened. And he conjectured that for any P group, this equality happened. Not only this equality happened. And with respect to that, what he did, he considered the Heisenberg group of order PQ, and he proved that, well, the result is true for prime congruent to 3 modulo 4. That much is his result. But what we observe is that the Heisenberg P group is a 2-generated, P group of nilpotency class 2. So we consider the all possible, classification, and we find that these are the all possible classification. G1, G2, G3, and G4. That representation is not known. It has given by Bacon and Capet. So we prove that we not only prove this, we prove that the Lowy length, the precise value of the Lowy length corresponding to G1. And for the lower bound, we face the problem. But if we take the gamma equal to 1, we have this equality. We exactly find out the ordered small Davenport constant for G1. For gamma equal to 1, corresponding to G2 also we get this equality. For sigma equal to 1, we will corresponding to G3, we got this equality. So we got this result, and this is irrespective of any prime. So it is not stick to P congruent to 3 modulo 4, even we are considering all possible primes here. Well, here are certain problems which I wanted to point it out that one can try. So this, I find that this is a very interesting question, whether this really true for, every classes of non-abelian group or not. If not all, then for which classes is there, we can classify it or not. For me, it's very interesting to study the combinatorial invariance for this kind of groups. Okay, and one side it's a P group and another side is a C3. It's a semi-direct product of that. Okay. Similar kind of question one may ask for the ordered Davenport constant, that what happened in case of the ordered setup, whether this kind of relation holds for the ordered setup or not. And most importantly, I believe that there is a very nice connection with the non-abelian and abelian setup, because you have observed that whenever I'm getting, for the rank 2 case, at least for the rank 2 case, when I'm abelian group, I'm considering Cm cross Cn. The corresponding Davenport constant is m plus n minus 1. And if I consider the similar kind of thing, like Cm semidirects Cm, we are, metacyclic cases, we are getting that in the sum of the cases, it will be like similar result it's giving. Possibly for rank 2 case, it's all over giving the same result. But to establish that that is true is really hard. So yeah, one can try on that direction also. Well, these are the references. Yeah. Thanks a lot.
Thank you very much. Are there any questions for Eshita? If not, we thank you again. And our next talk will be in about 5 minutes.
Thank you.